So there are some very obvious reasons why climates would change with regard to temperature and surface temperatures. One of them is if a landmass entirely relocated, for instance, from the equator towards the poles, and that's what has happened over the course of about 300 million years to our continents. For instance, going back in time, and I'll show you how we know this. For example, the geology suggests that all of the land masses today, the continents, were all one big landmass called Pangaea before. It was located kind of near the equator, kind of maybe a little bit south and of the equator, and they all kind of spread apart. So as these, for instance, these land masses moved towards the poles, of course, their climates would get cooler. So this is kind of Pangaea breaking up into continents that we now know today. And can you see where this actually part of South America, Africa, and India and Australia were all down here near the South Pole. And then, of course, with plate tectonics, they moved. And what plate tectonics are, I guess I should remind you, I think we talked about this earlier in this course. Plate tectonics is the theory that, plate tectonics is the theory that the Earth's crust is broken up into plates, and these plates move along the liquid portion of the mantle underneath them. So a very slow process, but definitely we get these locations will have different climates as they move. Isn't that neat? Another thing that will give us different, how the Earth is receiving energy from the sun will change as the Earth changes its position as it orbits the sun. So for instance, we know that all the planets, including the Earth, orbit the sun in a shape called an ellipse. Now, ellipses are basically ovals. So there are kind of flattened out ovals with high eccentricity, and then there are ovals that look almost like a circle with low eccentricity. And now as that kind of oval shape of the Earth's orbit about the sun changes, as its eccentricity changes slightly, then that means at perihelion, when it's closest to the sun, it's going to be different than, and also when it's at aphelion, it's also going to be different depending upon its eccentricity. So this is just to say that the shape of the Earth's orbit, its eccentricity changes, and so will then the amount of how the Earth receives radiation from the sun. Another thing is we talked about the fact that the Earth's axis of rotation is tilted 23.5 degrees, and but it isn't always 23.5 degrees. Actually, it kind of varies from a low tilt of 22 degrees to a high tilt of 24 degrees. So as its axis, the Earth's axis of rotation tilts a little bit, we know how important that is to seasons, and so also that will have certain consequences to how the Earth, again, receives radiation from the sun at its various latitudes. We call that as the Earth kind of fluctuates between its tilt, that's obliquity. And then the last one is if you think of the Earth keeping its 23.5 degree tilt, but if you kind of think of it as kind of making a coning shape, this takes, I think, about 26,000 years. And this will have its consequences as well. I may have talked about this before, but the Earth's axis of rotation is basically if you take the north axis of rotation and extend it out to a star clear out there, it would extend right now and point to Polaris. But like you can see from this slide, given, I don't know, 13,000 years or so, 12,000 years, it's going to point towards the star called Vega. And it's kind of a coning shape. It will still keep the tilt, but it will point towards a different star. So eccentricity, obliquity, and we call that last one precession, kind of the wobble of the Earth's axis of rotation. Those all three have consequences. And Milankovitch cycles basically kind of tie those three in and come up with an overall grand consequence of eccentricity, obliquity, and precession. Okay, so Milankovitch cycles kind of look at how these all kind of work together. And so we end up predicting, Milankovitch cycles predict cooling will coincide in these years that you see down here, 19,000 years, 23,000, 41,000, and 100,000 years. So if we kind of look back at the data, and honestly, I can't necessarily unpack this for you, but just to highlight what you're looking at, I'm going to show you 3 graphs. And each of the graphs, this is the present time over here. Okay, so as you look from right back to left, you are looking back in time. And this first one it looks the noisiest, and it is goes back the farthest. So these are millions of years. So this would be 5 million years ago. You know, this would be 2 million years ago, and this would be the present. And if we just kind of think along the y-axis, if we just kind of think of this as temperature, and this is warm, and this is cold. So that's millions of years, kind of honing in now. This goes back thousands of years, but it's like 200,000 years ago, 500,000 years ago, and 800,000 years ago. Again, this is warm and this is cooler. So, I mean, the Earth's temperatures have just, surface temperatures have just kind of fluctuated. They kind of do their own thing. And this is going back even, again, thousands of years, but it's a smaller scale. So this is thousands of years. So this, again, is the present. And so this would be 30,000 years, you know, 100,000 years, 150,000 years. So another reason that we get differences in our surface temperature could be solar output. Now, the sun is pretty darn regular right now. It is what we call a main sequence star, which means that it's kind of settled into being pretty darn regular. But it does go through an 11-year cycle. And in order to kind of gauge where it's at in this 11-year cycle, what we do is we look at its sunspot activity, its sunspots. Now, if you've ever heard of solar flares or coronal mass ejection or coronal holes, those things I just mentioned, and sunspots, those things all kind of go together to describe an active sun. And when the sun is active, and again, this is like an 11-year cycle, we do tend to get a little extra amount of solar radiation from the sun. I've heard it described, though, that it can't necessarily affect a change in our day-to-day surface temperatures. You know, right now in the spring of 2012, we're kind of ramping up for a solar maximum in March 2013. So is that why it's kind of warm this time of the year? No, I don't think so. But it was known that actually there was a time called the mini ice age, or little ice age, I think it was. And back in the year 1645 to 1715, there were not, you know, that 11-year cycle you're going to see here in a minute was broken. So there were basically not very many sunspots. So when we call it not very many sunspots, we call that a sunspot minimum. So this is called the Maunder minimum. And it was kind of a cold time on the Earth. So, so what you're looking at here along the y-axis are sunspots. And so just kind of generally think we have a lot of sunspots up here, not much sunspots here. Here's that Maunder minimum I was saying, that little ice age. And then can you kind of see the 11-year cycle, usually taking out the Maunder minimum. And so like I said here, I believe March 2013, they're still looking at this solar cycle to peak. So there's a close-up of the surface of the sun, and you can kind of see the granules. That reminds me of kind of like a beehive or a honeycomb. So that kind of granules here, these are always there, but that sunspot is an indication of an active sun. Sometimes sunspots come in groups. So this is a sunspot group, and you can see the sunspot individual over here. They're kind of cooler regions on the sun, but again, they're kind of associated with more solar output for us. So here we go. This is you can kind of see the 11-year cycle right here. Now, Just kind of a side note, I think I mentioned this earlier when we were talking about the layers of the Earth's atmosphere, and we can have auroras, and northern lights in our upper atmosphere. That when the sun is active, when we have a lot of sunspots, we have a lot of solar flares and maybe even coronal mass ejections, and then we get those charged particles headed our way. That's kind of how that all works together.